Welcome everybody. Glad you made it for one last try on this class.
Last try? I can't say last try.
Well, you know, I mean, I guess after this we can do more in person and personally if you want, but welcome everybody. So, you know, I saw this picture posted once a long time ago and I thought, this looks pretty cool. I wonder if this actually works. And so I thought I'd dig into it and try to find out if an antenna really like that really does work. This guy is in the Polish army, you know, back in the 1920s or something, and when they actually had photography. And he was walking around with that thing. And I say, I don't know if he's actually operating with it on his back or he had to take it off to do it. I don't know. But there was not a lot of explanation. But I did find a plan for that very antenna. And so I decided to make one just like that. And here it is. And there's some secrets to this antenna, but it's not exactly perfect. I mean, I was able to communicate over 100 feet with this, but you know, outside of that, you know, but I mean, I had to build my own transformer with it there. You know, what this is actually turns out, if you look at it closely, the driving element here is only this red thing. So this right here, it's very Christmassy, don't you think? Huh? So this red wire is the only element that's driving, and this is a kind of a delta loop for a Yagi, and then the rest of these are parasitic, and this is just a one continuous spiral. And no, it actually does kind of work. It's not the best performing antenna, and I did make a contact across the state, but still it's not wonderful, but it did seem to work. I had to get it up way high. You know, I remember when I was a kid, I used to make paper airplanes, and I mean, they were so poor that, I mean, I would really have to hook these things. You know, it would go like across the room, right? And my dad said, well, you know, if you throw a toaster hard enough, it'll go across the room too. So to your point, yeah. But at any rate, so I thought it was kind of a fun antenna. I wouldn't recommend it, but I had to try it and see if it actually worked. And
so what would make it better? If you could just, same design, but improve, would you space the wires further apart? Would you different transformer?
Number one, I would change the design.
Use a different one. Use a different antenna.
Yeah, this loop is just not a very good design in my opinion, because you got too much coupling, too much crosstalk, okay? And these guys right here are just way too close together. I would put them a lot farther apart, which would therefore make it more, you know.
Is there math calculations to guesstimate that distance? What
Yeah.
would be optimal or more optimal?
Yeah, you can sit down and figure things like that out. I don't know off the top of my head. I don't have anything memorized, but I mean, you stop and think about what frequency you're on, you can, you know.
Space things out.
That's right. Think about what's coupling it, what's not. Who are you? How'd you sneak in?
I'm his mom.
Hi, Mom. What's your name?
Cardlin.
Cardlin?
Yeah, my husband couldn't make it, so.
Okay. I remember your face. What's your name? Andrew. Andrew, okay. And Cardlin. Okay, I'm going to struggle with that name, but.
You remember Andrew? He's the one in.
Yeah, well, okay. I will try to remember both. All right, very good. Anyway, so much for this antenna. I had some high hopes for him, you know, portable, 20 meters, by the way.
So that's a 20-meter antenna?
Yeah, that is a 20-meter antenna. Yes, sir.
Yes, I had wondered, because I was talking with another experienced person as well who's experienced with antennas, but not loop antennas.
Yeah.
And he was saying that when you increase the surface area of a loop antenna, that will increase the bandwidth. I thought he was saying the resistance, and then he was saying something about the velocity factor. But from what I have read, if you increase the surface area, that will make it so you can run more power through it, but like increasing the surface area won't increase the bandwidth, and then adding more turns would decrease the bandwidth because of increasing the inductive reactance, but I'm not sure who's correct on this.
So what Sabra just asked, in case you didn't hear, was that she has heard that increasing the surface area of an antenna element, such as a mag loop and so forth, will actually increase the bandwidth, and then also it'll increase what now you said? Oh, the power,
Yes,
the capability.
I mean, I know for vertical antennas, that's true, but I thought for a loop antenna, increasing the surface area will allow you to run more power through it without it all being converted to heat, but that the bandwidth will actually stay the same or it will decrease if you add more turns to it. But someone else is insisting the opposite, and I'm actually getting very annoyed.
Okay, so yes, for almost any antenna, increasing the size of the element will actually increase the bandwidth too. And that goes for dipoles as well as loops, so that works just as well. And as far as power capability, that's true too to a small amount because you got the skin effect, and so it's kind of spread out. You have more power capability. So yes, those are all true about.
What about adding more turns to it?
Turns to what?
Loop antenna.
All I can think of, I don't know. I'll put it that way.
Decrease the bandwidth because of the inductive reactance.
Well, I don't know about bandwidth, but when you put more turns on a loop antenna, that will tend to decouple it. And so what you want to do is make it into a spiral, which, you know, I've seen antennas like that where you have a, oops, wrong thing. So when you have a loop antenna that's in one circle, that's one way to do it. And if you have another circle that's really close to it, you know, that will actually end up coupling too much. But if you can make it into a spiral, that will actually work better. And spiral antennas do exist, but there's a lot of caveats with that, and you got to know kind of how to work. Because this distance between here and here has to be, you know, like a quarter wavelength. And if you're going to make it on 20 meters, that means that quarter wavelength, we're talking about, you know, 16, 17 feet long. So it's kind of a very awkward antenna. But yeah, that'll work, absolutely. All right. I don't think it'll fit in your apartment. Anyway, this is the Wi-Fi password and access here in this place. So if you got that, there you go. And several people were asking about it for their phones and so forth. And there you go. I'm getting really good at this.
Has anybody been able to get on that?
It's not on.
Yeah.
I did.
Because it comes up with the unified guest login.
Yeah, and
that's
then-
it. But
well-
the button is not active.
You have
No.
to, there's a I accept radio button.
So
See,
there's a little,
It still didn't work.
check that radio button.
so there's a little check mark to the left of
Got
it.
it.
Yeah.
And,
And then
be
that's
aware
it.
that that's my connection to the YouTube stream, so don't use it unless you need to.
Like, don't be downloading stuff.
Okay.
Yeah.
All right. Very good. Okay. Let's see. Last week we talked about coupling. You know, there is one thing I want to make sure of that, and I kind of mentioned this on Facebook, and there was a question that was asked last time, and I failed to answer that question, and about in-fed antennas. It was an important question, I feel, so that's why I wanted to really answer this. And that is, if I have, and I'm going to kind of exaggerate and blow this up a bit so you can see what's going on. First of all, let me just remind you about Harvey, my beautiful dipole. And if you look at Harvey, again, what you see is that there are, well, except for Sabra, sorry Sabra, but there are, you know, two sides of this dipole, right? And there's not a positive or negative to this, even though one's connected to the coax shield, one's connected to the center connector. There's not a positive or negative. It's all AC, so there's going to be both positive and both negative. However, if I was to cut off one of these elements, just totally lop it off, that's an end-fed right there. Will it work?
Yep. Yes.
Heck yeah, it will work. But there are caveats to it, okay? It won't be quite as good as if with a full dipole because it's missing that other half. So if it works, well, how does that work then without that other half in there?
Half signal.
Say again?
Half the signal.
Half the signal? Half the signal going out, right? And does it have the signal come back? Yeah, maybe so, you know. Well, what's going on though is that this is exactly how end-feds work, is without that other half, we've just simply lopped it off. And yet we buy these things from MFJ and DX Engineering and expect it just to work right out of the box because they make good antennas, and end-feds we know work because I've worked them and people have done magical things with them. The question was though, how do they work? Because it's like, well, okay, the real question was, do they need a counterpoise? And that was the part of the question that needs to be answered. So if you, and this goes back to common mode current, and these two are really coupled together, no pun intended. So I'm going to again look at the coax like this. I'm going to take my coax, blow it up a bit, and just take a look at only the center conductor here and the shielding. And in between that, the shielding and the center conductor is the dielectric. And the dielectric is nothing but foam or plastic or something that's non-conductive. And that provides the capacitance for the coax. Now, and again, to reiterate, we have a signal that's going on the outside of the center conductor and on the inside of the shield, and that's due to the skin effect. And the skin effect occurs because of eddy currents inside the metal on high frequencies. When it's lower frequencies, you don't see that quite so much. But the higher the frequency, the thinner that skin. And so the thinner the skin, then you can afford to have, really thin conductors. That's why you find a lot of old TV antennas and such that has these tubes, right? These aluminum tubes that are made of, because they don't need the center part of it because it's kind of a waste, right? The current only flows on the outside because of the skin effect. Anyway, so that's why they have that. So on the coax now, here's where our end-fed comes in. As we know, this is going to feed into our unan, and our unan has our toroid and so forth, and he's going to come in here and wrap around, blah, 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 and eventually he's going to magically come out, and there's our antenna, and this is our element. When I say element, I'm talking about any conductive thing that's going to be the radiating part of our antenna, and this is our unan here. And the question was, well, okay, there's one side, but where's the other side? And that's a question I feel it was so important we have to answer it in here. Because remember on Harvey, okay, the dipole we got here, and here's our coax coming down like this. What we've got is that as the signal is coming through one side of the coax, and the current is moving in this direction like this, then the current is also moving in this direction because this is AC, right? And so one is going in the center conductor of the coax, one is going in the shield, and we're going back and forth. So every half cycle we're switching directions, and that's how that works. But when there's not this side over here, well then it still has to work, because the AC still has to come down here, but where does it come from? That's kind of hard to, you can't get something from nothing though, right? So that's what I want you to understand, and this is really important because I don't want this to happen to you. It's not terrible, but still. So what's going on here is that let's say that the signal is coming from, sorry if I'm standing in front of you, signal is coming from here into this unan. Okay, this is got to be connected too, right? So it's connected magically into part of that as well. Then this other signal will come back down in this as well. But the thing is, there is nothing for the signal to come back from because the current isn't coming from anywhere. And so what's going on is that instead of this signal coming back from the inside of the shield, like I mentioned, now what you've got is a signal on the outside of the shield. So the outside of the shield of the coax is making up for that difference, and that's where the other side of that dipole is. And this other side of this dipole for an end-fed is on the outside of the shield, and you don't want that in your coax. The reason you don't want so when you've got equal and opposite currents like this flowing on the inside of the shield and on the outside of the center conductor, that's called differential current. Differential because they're equal and opposite. That's what we call it in engineering. Blah 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 blah. Okay, but when it's on the outside, then that means that this current flows in this way and a current flows in this way as well. And it's like, how can you do that with current flowing in the same direction on the same conductor, but they're two different currents, okay? And that's called common mode. So they're commonly in a common direction, and this is called common mode current. And so when you have this kind of situation, this is not good because all the electric field that these two produce are confined within inside the dielectric, and so it's enclosed. But on this one here, this thing, because it's not on the inside, this will radiate. And because end-feds radiate through the coax, that's when you get that effect that my friend had with his wife with his recliner, right, and so forth, and your TV starts flickering. You can start hearing your signal through computer speakers and on and on. And these things will come through because of your end-fed acting like this. It has to go somewhere, okay? And so it's going to end up on the outside of your coax. Not a good thing. So we do two things to mitigate that, Mark. John.
Most electrical circuits, okay, have a closed loop, okay? But the antenna right, is not a closed loop, okay?
That's right.
So this is what you're talking about, okay, as far as the, the feedback or whatever you want to call it, okay, the pulse that comes back, because it's not terminated the right way, right?
Termination is part of the problem, but yeah, because of the feed point impedance, right?
Yeah.
Okay. Okay, so yeah, that's good addition. Thank you, John. I've called you Mark this whole time. Why didn't you tell me that last week? Thanks, Bob. Okay, so, all right. So this current then will radiate outward like this, and that's not a good thing. And when this does radiate, then what you've got is RFI, which is radio frequency interference. That's supposed to be an F. And other kinds of interference. And this is going to just cause havoc to your neighbors. This is when they come knocking on your door and so forth. Anyway, so that's what you want to take care of. And the way to take care of common mode current, two things you got to do. Number one is you need to add a place for this to go. So in other words, a counterpoise. Counterpoise has a couple different purposes, and this is one of them. And this one means to add this section here for the for this current to go. However, your counterpoise doesn't have to be humongously long. All right, and I mentioned last time that you can have a long counterpoise for like 80 meters, and that's great and so forth, and that'll take care of a lot of things. But if you have, in fact, here's my rule of thumb. If you have an 80 meter end fed, then your counterpoise should be about 17 feet long. If it's 40 meters, it's about 13 feet long. 20 meters, it's about 7 feet long. And that's about a good, length for a counterpoise. And what a counterpoise is simply hooked to the ground section of this guy. There's a little ground wing nut sticking out there. Hook it to that, and your counterpoise. And the next question people ask is, well, where do you put it? And I would put it as much as you can underneath the radiating element alongside of it. Put it along the dirt, just on the ground, somewhere underneath him. If you can't do that, well, put it somewhere else, okay? But the best you can, closest you can to your radiating element. So that's kind of ideal. Rick?
What would happen if you hooked up the antenna the other way, though, and instead of using the center conductor, use the shield, and then how would the same requirement happen for the counterpoise on the center conductor? Because you don't have the two sides have the same skin effect, do you?
So you know how to answer that question, Rick, because you know the signal coming through here is not DC, but it's
AC.
And that means it's equal and opposite.
Right.
So it doesn't make any difference.
But usually your antenna length is longer than your counterpoise length.
Yes, it is. But whether it's hooked to one or the other, it's a conductor. And your coax isn't going to know the difference.
Oh, okay.
It's just carrying AC.
Gotcha.
One way or the other, it doesn't know.
So yeah, even though you might be sending to the element from the shield,
Yeah,
it's as the signal's coming back, it would still find the outer shell of the.
that's right.
Okay.
Yeah, and in fact, I knew a guy who made an onion like that, and he accidentally hooked the shield part to the other side, and he kind of goes, oh my gosh, I got to do it over again. So he started tearing it apart. I'm going, dude, wait, this is AC we're talking about, so it doesn't have to do that.
Okay.
Sabra.
Convention says we do it, the center pin is the plotter or the driven link.
It's just a habit. Yeah, I do
That's how we
that.
talk about it, it's really just, oh.
Exactly, it's identical. Hi, Sabra?
Yes, I had a comment and a question. Firstly, I've noticed that with copper mesh, you don't want to get too much surface area, but if you use like 4 or 5 inches across instead of a wire, you can get away with making the ground plane shorter, and also you can drape it so that even if it's not perfectly flat, it's still like I was able to get a good SWR, like of 1.5 to 1, and it takes up a lot less space, so you can still have a ground plane. Like this one's for 10 meters, but I could probably fit one twice to 3 times as long. So you can actually do that if you're short on space, that copper mesh, and you cut it. And then the other question, I had a question. This is about the J-pole antenna. I know that we're focused on HF, but you had said that you were talking about common mode current. The instructions had said that you need to put a choke on it, like a big Ballon type choke, so that the common mode current will not interfere. But I wasn't sure if that's for long cables, because I had thought you could get like a very small thin cable and just put some ferrite beads on it, especially for indoor use. Or is that not enough, or does it depend on the power?
Okay, first the comment. Number one, you're addressing ground planes and with a mesh and so forth. And if you use a mesh for a counterpoise for an antenna, like I'm talking about, like an end-fed, that does work as long as you don't make it too big.
Yeah.
So yes, you're right, that mesh will actually work. There are some caveats to it, because if you make the mesh too large, it becomes unwieldy, especially in an apartment situation like you're talking about.
Yeah.
So if you use just use some sense on that. I think that you can figure that out, and you have, and that's good. Now the other thing about the choke on the VHF antenna, whether it's a J-pole or something else, J-pole is subject to a lot of common mode current. That's just its own nature, because it's an unbalanced antenna. Any unbalanced antenna is subject to, is prone to produce common mode current. And so what we end up doing is we make the, as I'm trying to erase here, we make the J-pole with an RF choke below that. And does every J-pole need this? So what I've just drawn, Sabra, is a wire that's gone below the J-pole. It's hooked directly to the J-pole, but it's in a coil of about 6 to 8 inches in diameter and about 6 turns. And this is an air choke.
That's what I'm talking about.
That's right.
But that's not the feed cable from the antenna. That's a separate.
Nope. This is
That is the feed cable.
that's right. This is the actual feed line that's coming from the antenna. Absolutely. And I've done this with all my antennas on my roof, whether they need it or not. And people ask, well, do I need one? Well, if you got, a lot of interference, if people say, you got this 120 hertz hum, that'll solve that. But
I was wondering though, you don't want the common mode current interfering with smoke detectors, but let's say you have a 3-foot cable. Do you really need that big choke, or would putting a few ferrite beads on it fix it?
is the problem there or not? Well, if it is, then you need one. If it's not, you don't. However, if it's interfering with your smoke detectors, what you find out inside them, they don't have a lot of really smart circuitry to prevent or filter out stuff like what we're talking about. So what you want to do is put a 0.01 microfarad capacitor across. And it doesn't matter if it's AC or DC, okay? If you got some smoke detectors, like one I have at my house, it's an AC detector. My previous house, it was battery, so it was DC. And they're both prone to interference by my radios. And so when you put one of these across your power, AC or DC, that should choke it off, because that frequency, I'm not going to go through the calculation. I did it online somewhere, but is good enough for 2 meters. 70 centimeters, not quite so much, but
It's there, it'll take up some of the...
That's right. It will take up some of the energy.
I haven't had problems. Mine are just electrically wired in, but since I haven't used a J-pole antenna that much, and I wasn't sure if you specifically need the choke to block the common mode current, or if the ferrite beads snapped onto the cable would block it.
Ferrite beads can be effective, but at 2 meters, it's not quite as effective as an air choke. So air chokes are made for a much higher frequency than what you need for the ferrite beads. Ferrite beads are great. If they do work, great, but what?
I wasn't sure if the cable length or the power actually affected it, like a 3-foot cable versus a 50-foot cable.
It's not the power, and it's not the cable length. It's the whether the antenna is balanced or not. That's what affects common mode current. Okay, and And now that you mention it, of course, the let's see. Besides the capacitor, what did you say? You said something about the.
Like, if you put 4 or 5 ferrite beads on
Oh,
the cable,
that's what it was.
as effective as it should.
Well, one thing you can do is add a toroid instead of a ferrite bead. And you do a toroid like that, and you can wrap your coax like that around your ferrite, and that should do it. But this ferrite toroid that should do the trick as well for 2 meters. It's not always as effective as the air coil is, but this can work in many instances. In fact, if you do this will work really well on 12 meters and 10 meters, a little lower frequency than 2 meters. But at any rate, so the experiment is the only way to know for sure.
Is there a best distance from your antenna to the J-pole for that choke to be placed?
So Joe is asking, is there an ideal distance that you should place your choke between, well, your choke and your antenna? And to me, the best distance is as close as you can, because whatever distance you have between the choke and the antenna is what's allowed to radiate. So to minimize that means minimizing the radiation. So there you go.
I mean, like, I have a choke on it right now. I don't want to find out.
What's your name?
Harold?
Harold. Okay, so Harold, let me take your question and then back to Sabra.
So you're talking about the counterpoise and
Yeah.
letting it go underneath the element
Yep.
on the ground. There's an antenna system out called the POTA Performer.
Okay.
And he talks about them being raised about 1 meter off the ground.
If it works for him, wonderful.
Is there an advantage to that?
Sometimes when it depends on the ground soil. So here in Utah, our soil conductivity is so poor that it's not going to make much difference. If you do it in Georgia, where the soil conductivity is really good, okay, then it can really help a lot because the soil acts as a capacitive load on that thing. So yeah, it might work really well. So I don't know where this guy is.
Well, he says he's picking up like 4 to 8 dBi by making them raised
Okay.
off the ground, and I'm sitting there thinking, so what difference does that make actually? But it would have to do with the conductivity.
It does. It really does. And there are other things too. The band conditions can actually affect that. You can have poor band conditions and you could drop that thing down, but work really well, or bring it back up in the band conditions, and it depends on the frequency. So a lot of things are ifs. So, yeah. Were you going to say something, Sabra?
Yes, sorry, I don't want to get too off topic, so
What?
that'll be my last.
You
comment, but
you off topic?
I had, I had this very tiny 3-foot thin cable that would be perfect, but I'm using a bigger, thicker cable with that choke on it, and I don't like it, especially for indoor use. But if I'm stuck with it for the J-pole, I'm like, why can't I just use that thinner one and just put ferrite beads on it?
I would take the ferrite beads off of it and just use a thinner cable.
So you think the thinner, I don't need this huge cable with a huge choke. I don't like it, but I'm like, I don't want the common mode current to interfere with anything.
If I'm envisioning what you have correctly, then yes, you don't need that.
It would be a jumper cable for most people, but it's like 3 feet. And
Yeah.
I don't need it that long.
I agree. All right.
Can I ask one more question on this?
Of course. No, yeah, that's fine.
The more power you push, the more RFI you get off on that common mode component.
Yes. Yeah, linearly, if you
100
do...
watts, you're going to get more RFI on the common mode side because you have more power.
That's true, yes. More power means...
Which
And
means
it's...
the choke becomes more important.
Yeah, and linearly, I guess that's the case, yes. I'm thinking of more frequency, and higher the frequency, then it really jumps up as your frequency goes up. But yes, you're absolutely right. All right.
So maybe to answer part of Saber's question
Yeah.
then is, if you're on a 5-watt handheld, common mode current's not really going to be a problem because you're not pushing out enough power for it to generate enough interference coming back.
Even on 5 watts,
On
I've
VHF.
seen... No, yeah. I've seen 5-watt VHF be a problem,
Okay.
for common mode current on a J-pole. And really, if one of the things I've seen is just get the J-pole away from the rest of the radio, and that helps a little bit, okay? But a coil helps a lot. So, yeah.
The coil then, even though it's annoying.
Make your coil, Sabra. All right.
Or make a little box with a short range one in it that just screws onto your J pole and then onto your feed line.
Yeah, like an ugly ballon. That's the same kind of thing, because it's an air coil. All right, what was I trying to answer with this?
You're doing ways of solving the common.
Or what
Common mode current, that's right. Okay, good, thank you. So the way to solve common mode current here is with the counterpoise. That's one way. That takes the signal so that it has some place to go. And the other one is with a choke. And dang, it looks like we've already covered that. And when we're talking about choke, okay, I'm not talking about an unun so much. Okay, I'm talking about like a one-to-one ballon or unun, whatever applies. In this case, probably just an unun. But a one-to-one, and it's like, well, wait a minute, what advantage do I have by transforming a one-to-one? It doesn't give me any advantage, right? Well, not impedance-wise, because this ratio is meant for more for impedance when we're talking about a 49-to-1, remember, and so forth. Okay, but this guy here doesn't transform impedance. What it does is it chokes off common mode current. That's its whole purpose. And when you do that, then that leaves the impedance alone. That's what the one-and-one's for. But at the same time, it takes care of all the common mode current coming back into the shack. So with this guy right here that's coming down on the outside of the coax will be stopped right there at your one-to-one. And also, this is called an isolator. Some companies, who calls it that? Oh yeah, Bellin Designs, and there are several people that call it an isolator, and that's what that is simply a one-to-one Bellin. And they work really well. One of them is the MFJ 913, and that's a nice one-to-one, and I use that once in a while. And not every time, but just if I ever have a problem with common mode, then I use that. Anyway, so there you go.
Just to reference to Noji, you're saying a specific model number. You can't make them. They're not hard.
Oh man, they're so easy to make. Yeah.
Some RG
Yeah.
58 and
You can do it with coax depending on the frequency. That's right. I like to use toroids because I focus on
But again,
HF.
you can acquire the toroids and the enamel wire, and they're easy to make.
Yeah, absolutely. Vern, or who was it that had the hand over here? Scratching noses? All right, very good. Okay.
Well, Noji, sometimes you hear about people saying with the choke, you said that you prefer to have it right next to the ballon or the unun that you have. And I've heard others say, well, put it right next to the radio.
Oh, okay.
Then your
Feed line.
coax is carrying all that current, right?
That's right, it's
So it
radiating.
is another radiator.
That's right. It's radiating, yep.
So it definitely should be next to the transformer or the element.
But next to the antenna as close as possible. That's where you want it.
Having more than one ineffective? Like if you put one at your radio and one at your antenna?
I've been asked that a few times, and you know,
Experiment, find out.
yeah. I mean, really, I've never used them like that. You know, more than one, but why not?
Just guarantee that the coax is not carrying any more than it has to.
Well, what you got to consider is that, number one, if the performance is there, you're great. Does it have too much loss? I don't know. Play with it and find out. Like I said, I've never used it like that, and never really needed to, because when I've done like POTA things, I just use one, gone out there, it works like a charm. So, yeah.
So as far as positioning it, in my home base station, I have the unun right at the base of the antenna. It feeds one of the antenna. When I do like a mobile or a POTA operation, I actually put that at my transmitter, and I do let the skin effect of the outside braid just act as a counterpoise.
Okay.
That makes sense, right?
So you can do that, just have to understand the consequences. So you can do it without any counterpoise at all. It'll work just fine. It might do better with it, that's all.
Right.
So yeah.
Yeah, it depends on the situation, if I'm compromised, if I can put one in or not, but
Sure.
otherwise I'm basically using the outside as a counterpoise.
Yeah, and many people do rely on that, and it's really not that big of a problem. It's when you run into problems, that's when you need to mitigate it. So yeah, many times it'll be just fine. I just wanted to mention really quickly the G5RV, because I get so many questions about it, because people love it and they hate it. It's like, and the biggest problem with G5RV is people don't really understand how to use it. And once you understand, then it's like, okay, now I know why I'm never going to use one. But anyway, this is a G5RV. It's simply 2 wires, and this is a dipole, and these 2 wires are equal length. I didn't draw them very equally, sorry, but I'm not an artist. I should have had Gary come up and do this. He's a great artist. But between this, then what you've got is a ladder line, or like window line. There you go. That looks like windows, right? And it's connected on one side and the other. There you go. And so when you got this set up like this, there's a couple problems that's going on. Number one, if you do the G5RV, I'll write it down here. G5RV. Sorry, they didn't have to make a slide for that. Trevor, apologize. But G5RV antenna, it's a wonderful antenna. If you could do this right, this thing like outperforms just about anything. It's just very, very nice antenna. Let's see. But the problem with this antenna is this ladder line right here. I mean, the ladder line is easy to get. You can get it on Amazon and tons of places. The problem with it is this little portion right there.
Terminated?
Yeah, well.
Or connected to your connector?
It's its proximity to things, okay? So what happens is I go to people's houses, they say, look, I've got this G5RV, I bought this, and it's just garbage. No one gives me, I can hear stuff, but they can't hear me, and I can't make any contact. My SWR is like 1.2, you know, it's like, great. Okay, so, and I look at their G5RV, and what's going on is that what they've got is this bottom section is sitting there draped on the ground. Okay, and it's finally connected to maybe coax or something, and then it goes into their house. And this little connection by coax, by the way, is typically by a balun. Anyway, some kind of termination, so that what we're doing is we're converting this balance to an unbalance. This ladder line's balanced, so this is truly a balun here. And when they do that, this is fine, except for the fact that this part here lying on the ground is coupling with the ground. So you can do that with coax. You can't do that with ladder line. Because again, ladder line is this parallel thing. Its wires are exposed. Well, kind of. And so because of that, there's proximity to...
Shielding each other.
Yeah.
Like coax.
And it is, coupling with that ground. And so naturally it's not going to work. I said what you got to do is get that thing so that the bottom, that isolator or whatever, the balun, is at least 8 feet off the ground. They're going, wait a minute. If that's 8 feet off the ground, and this thing is typically like 41 feet tall, 41 plus 8, that means this antenna's center section, this right here has to be almost 50 feet off the ground, okay? I'm going, yep. They're going, I can't do that. I says, well then don't use a G5RV. I mean, so that's the problem with it, okay? And the coupling with this and everything else.
How, like, say, if you got that on the top of the tower,
Yeah.
how far away from the tower do you think it needs to be so you don't get that coupling effect?
So the answer to your question is what? This or this?
The ladder line, yeah.
Yeah, so,
How far off? I had one of these in my previous house, and
Yeah.
I think I had it out, I don't know, a couple feet on some pretty stiff PVC that I used.
Yeah.
And it went down. And it seemed to work okay. I was just wondering if I was having problems with that or not.
so it's frequency dependent.
Okay.
That makes sense?
Yeah.
Because what happens is if you get that thing coupled or too close to your tower or your shed or your swing set, or your dog, or whatever, those things will couple together depending on the frequency. And the higher the frequency, the closer they're going to be to start coupling. And so for 2 meters, I would get them farther away, and then higher frequency. Anyway. So what you want to do is get them far enough away. For most G5RV supports 80 meters. Okay, if you're gonna work the whole bands, okay, I would get it at least 6 to 8 feet away from anything. I mean, that means this thing right here, 6 to 8 feet away from anything metal.
I don't understand the question. Far away from
From anything metallic that will couple with it.
Yeah.
So when you
Oh, it's a standoff.
Yeah, it came off horizontal.
So your standoff was like a foot?
Yeah, a foot or two, yeah.
Okay, so let's say 2 feet.
And then the ladder line was coming down parallel to the tower.
And that was a good setup?
It kind of worked, yeah. But
The important part was the end of the wire was not on the ground.
yeah, it wasn't on the end, but
And it wasn't on
It was
it
not
wasn't on
8
the
feet
tower
near
either.
either.
the tower was only 40 feet.
And did you have it set up horizontally or do you to turn it vertically?
The ladder line is vertical up, you know,
And then
basically
the-
paralleling the tower. And then I had it, the elements and vertically going down.
Yeah, if you set this thing up vertically, you're 135 feet in the air from this end to that end, right? And even if you do that, that's great. If you're counting on a vertical, orientation, but that means this end has to be 8 feet in the air too, which means 8 plus 135. That's a pretty tall antenna, okay?
Okay.
So yeah, this is typically a horizontally mounted antenna. Jim?
So your ladder line needs to be vertical and it needs to be up off the ground. Why not just shorten your ladder line?
You can, except for one thing. The length of this ladder line is made to adjust the feed point impedance. That's why it's a certain length. If you did cut it, you'd be great. But what you got to do is make up for it by adding some sort of impedance matching device there. Some sort of transformer or some other magic, Yeah, you can do a, 4-to-1, 9-to-1, whatever it takes. So yes.
So a ladder line is not like coax where the impedance does depend on the length.
That's right. Yeah, coax is pretty much frequency dependent, and that was from that first equation I showed you on that first day. But ladder line, no, it's. Wait, did I say that right? Coax is frequency independent. That's what I was trying to say. Ladder line is dependent.
Oh, okay.
Yeah, it's pretty coupley.
450 ohms, isn't it?
Yeah, well, this one for G5REs usually are 450. I made one that was actually a 300 ohm window line. It worked okay,
From a TV, the old ribbon TV.
Yeah. All right.
A little closer together, which
Now, some people say, well, gosh, I don't need 80 meters, so I'll just rely on the G5RV Junior, which is fine because then, your antenna is not, nearly as long, which is fine, but you still got to have this problem because this is still going to be not 41 feet, but about 31 feet. That's still a long ways off the ground, okay? But that's the biggest problem people have. The second problem, of course, is they get this thing way too close to their metal sheds and things. I just want to mention that about G5RV because it's always coming up. People always want to use it, and they are wonderful antennas, I promise you, if you do it right. And this is how you do it right. All right.
So really, if you didn't have a center mast, you'd need some string or something to put the elements up on and span between them and support the weight.
See, and that's the hard part too, is like, well, how do you suspend something that high in the air without metal? A tower is great, right? Well,
Now you're gonna have two towers, one for each end of the element. and
yeah.
then
So
screw
the
that.
way I did it on my property, okay, is I had 2 metal masts, okay, and they were military masts going way the heck up, right? And this thing was suspended like a super tight antenna. So it was,
The elements were on another kind of rope to support.
yeah, I had Maestrant that I used on pulleys. Okay, well, so those of you who don't know, okay, I'm in love with Maestrant. Maestrant is a guy wire type. It's inexpensive, but it's the greatest thing I've ever seen. It's better than Philly strand because it's much less expensive and will weather. This stuff is made of Dacron and a combination of things. So it came from the military, but the military doesn't use it because hams use it anyway. So, but this stuff is again made in the Ukraine. It's like these guys make good stuff. Anyway, Maestrant's really good stuff. Anyway, so what I've got is I have my guy wire here, and it's connected to a insulator, and there's my antenna. So my antenna element.
Or just use your finger, put your finger up there instead of your,
Is that how that works?
or 2 fingers maybe?
Huh? You got it. Good. Except look at that. Look at that.
Good enough.
But I'm gonna, if I go to bed tonight without that thing erased, I'm just gonna drive me nuts. No, just kidding. Anyways,
Now he has to know how to bug note.
that's right. Well, that's not the only way, but okay. So this is my antenna element, and this is just my Maestrant right here. The guy wire, hook it onto a pulley like this, and I'm against my house or a tree or whatever, and that's how I had it set up there. But I mean, this was really, really tight because it's 100 and whatever feet long, right? So you can do it that way. That's the only way I can get that middle thing off the ground without, getting it near anything conductive. So at any rate, but just little tips.
Got another question.
I got it off the thing.
So the
Oh, yeah,
main-
Don.
If it's made with like an artificial material, it doesn't become conductive if it gets wet then?
I have never seen Maestrant do anything bad when it rained,
Okay.
and I have Maestrant all over my antennas.
Okay.
So the answer to your question really is I don't know. Okay, but I've seen it rain and so forth many times on my Maestrant, never seen a problem. So
It's better than a metal guy wire to start with.
well, yeah, because metal guy wires, you're asking for trouble. But yeah, Don.
Okay, so the G5 RV, good news is DX Engineering will get me one for $89.95.
There you go.
But the other news is it's 102 feet long.
Okay, great.
The antenna elements plus the.
So that's not going to my apartment.
Well, what does it say that it supports though? Because maybe they've got some magic in there that's like a transformer that might help it. I don't know.
Yeah, it doesn't say, it just says it's 102 feet long. And minimum recommended feed point height, like you were getting at, is 35 feet. I guess off the ground, that's where it feeds into the center.
Okay, see, that sounds more like a G5 RV Junior, but that's not a
Oh,
Junior.
really? Okay, yeah, it just says G5 RV.
Okay, well, so, there you go. Yeah, if it works, great, as long as you follow the rules. Okay, we've got to move on here. And I get the right pin. There we go. Oh yeah, once upon a time we used to call this the rusty bolt effect, where you can actually pick up an AM station on your fence, because the AM station is radiating everywhere, right? And if you listen to your fence really closely, you can hear the station come through. Or if like Michael here, he's got his mouth open, he's full of fillings, you can hear the radio station come through. Okay, that's the rusty bolt effect, and this is because of coupling. And the Yagi antenna, strangely enough, works by that principle, that it not only couples, but it re-radiates. And I just want to make sure you understand this one principle too, that anytime that you have a piece of metal that's picking up any radio signal, it will re-radiate that same radio signal, and maybe at a different frequency. And that, again, is one of the principles by which a Yagi antenna is made. And that re-radiation catches people by surprise many times, because it's like, now you got this antenna in your house, not only feeding into your HF radio, but now your wife is picking it up on her computer speaker, And there's no common mode current. It's because of the re-radiation. Anyway, not going to go into a lot of math on that. There's all kinds of great books that you would never want to read. Anyway.
Is that why you have a director and a reflector on a Yagi then?
That's right. So the reflector is made so that it's about a 5% longer, and at the distance about a quarter wavelength away from the driven element, so that it can actually catch that signal, and at that length it'll re-radiate at that different frequency, and more specifically at a different phase. Okay, and it will actually couple with that signal going out one way and cancel going the other way.
So is there any advantage to having more than one reflector then?
People have experimented with dual reflectors. I've seen that before, but I haven't heard if that was truly an advantage, so I don't know. Directors, very definitely. So yeah.
Which of the ones with directors are mostly log periodic antennas then?
Say again?
So the log periodic antenna is an example of the one with directors and reflectors. Right?
Actually, a log periodic is a series of driven elements. They're all driven elements. They're all active, whereas Yagi only has one driven element. Everything else is parasitic. So same thing, only different. So yeah. Yeah, very. All right, before I move on, we just got to understand something quickly about the near field and far fields. And who was it that mentioned this last time, I think? Was it Mark? Okay. So,
because we had to do RF studies, for radiation.
That's right. And what I'm talking about when I mention near field and far field is, if I look at Harvey right here, I can examine the radiation pattern, maybe that's coming off right here, and it might be a little different than what it is here. And maybe it's going to be different than what it looks like off the end, okay? And the real question is, who cares? All right. Bill, welcome. Good to see you.
Good to be here.
Sorry if I didn't acknowledge you too, but Bill. Anyway, so most antennas, okay, we often don't need to care. So when we started this class 2 weeks ago, we did kind of care about those details about where on the antenna things were happening, because we were focusing on how antennas worked and the very details, and that's great. And that's called a near field, because we're near to the antenna, we're close to the details of what happens along the line, and we wanted to know, because this is what determined what radiation went out from our antenna and what was actually needed to be sent out to space so we can actually make radio. But now, all of a sudden, I'm going to take this antenna, I'm going to move it 5 miles that way. When you do that, well then suddenly this antenna doesn't look like a dipole anymore, it looks like this dot way down there. And that's called a far field point of view. So near field taking close proximity effects into account, far field is ignoring those close proximity things. So I don't care what the signal looks like here versus over here when I'm looking at far field. In fact, most of the things we deal with in amateur radio talk about the far field. Size of the antenna is large compared to that of the affected object. There we go. We're more often concerned with the far field. All right.
So maybe just an extreme example is a satellite dish or a parabolic dish close to your antenna is a near field effect, because it changes how that far field effect ends up, because it reflects all that radiation from one direction into
So
one direction.
what you're talking about is proximity, not far versus near field. If we're talking about a parabolic dish and the near field effects, we're talking about, well, is this, is the radiating element, going to be more, radiating more towards the back of the dish or more to the side of the dish? You see, that's a near field consideration. If it's 5 miles away, it's like, just looks like a blob to me. Okay, so that's the far field consideration. All right. I am going to now take my antenna here, with all due respect to Harvey, I'm going to move it miles away. And miles away, it's going to look like a dot. There it is, just like that. And so when it's that far away, I don't care what shape it is. I don't care what orientation it is. I don't care a lot about anything on this antenna. All I want to know is, well, okay, so what I'm going to do is, with my magic pen here, I'm going to draw a line indicating the relative power coming from that antenna at a certain angle. Okay? So I'm going to say, well, from this dot, it looks like to me, and how I know this is because I've got a power meter, what do they call that? A power meter. So, and I'm going to, thank you, field strength meter. And I'm going to take that field strength meter, I'm going to measure this thing right here. And I'm finding out that maybe it's about, I'm just going to draw a line that's, I'm making this up, okay? That's relative to how strong it is. I'm just going to say, starting with that, but I just moved that thing a little farther away. I'm finding out, oh my gosh, I've got, this thing's like twice as strong in that direction. And over here, maybe it's not even a blip, so not hardly anything at all. And over here, in this direction, maybe not very much, okay? But over in this direction, maybe a lot. It's like, oh my heck, what kind of antenna is this that does that? And then over here.
I have some that do that.
Yeah, I've made accidentally antennas that do that too. Okay, so I'm looking at this antenna, but there's more, because this is a two-dimensional drawing, and this is a three-dimensional antenna in a three-dimensional world. And so I've got out here maybe a line coming about this far, and another one over here. It's like really strong. So as I'm moving my field strength meter around my antenna, then I can detect how strong my antenna is in different places. And I'm going to draw lines out at each one of those different places to maybe get an idea of where my strengths of my antenna are. What do you think, Mike?
Doesn't the polarity of the antenna also affect those lines?
The orientation of the antenna determines the polarity many times. And
Right, but if it's
polarization.
5 miles away
Uh-huh.
and it's oriented one way, then you can measure your lines. But if you orient it another way, like take it horizontally
Right.
polarized, then your lines are going to all end up different. Isn't that correct?
That's correct. And so here I'm 5 miles away with Harvey, okay? And the person that sees this, I can't see what orientation I'm having this antenna. And I'm saying to, over to Aaron and says, which is it, horizontal or vertical? He goes, I don't know. I can't tell. I can't see that far. I have to put my glasses on, okay? But he's looking at the signals over here through his field strength meter. He goes, oh, it's a horizontal orientation, I can tell, because the signals are horizontally polarized. And I could do this, and he goes, oh, you just changed something, you know? And now, so he can tell from a distance, yeah.
And what you're drawing on the board is one perspective of the three-dimensional space.
That's right, absolutely. It's a slice.
Top down or from, yeah, slice.
Yeah, it's just, and
A given altitude at a given distance.
there's not even any top or bottom. It's just in space. It's like three-dimensional here, and it's just one cross-section of that space. In fact, what I'm going to do now is I'm going to draw a point-to-point. I'm good at point-to-point, so I can do that. So I'm taking my pen, and I'm going to draw point-to-point to this guy, what this thing kind of looks like to me. There we go. So what I'm drawing is a figure that's made of all these points connected together like a dot game here. And this is nothing, so I'm going to go back to nothing. And there you go. That looks really weird, okay? But if your antenna does this, and it can, okay, then this is known as an antenna pattern. And let me just tell you right now that your antenna pattern means everything to how your listeners will pick up your antenna. If you want to know if your antenna is working, your antenna pattern is going to tell you everything. Well, Jim's going, but how do I know what my antenna pattern is? You can walk around with your field strength meter and for 15 hours kind of figure that out, right? Like I just did here. Or, you know, you can model it. And so there are programs like Easy NEC and other programs that you can actually put, you know, and through some numbers and say, well, I've got this kind of antenna that's this long and this, and it asks you a bunch of questions. You know, you can put the parameters in, how high over the earth it is, all these things, how near to, you know, to Joe it is, just things like that. And once you put those parameters in, it'll come up with this pretty picture. And it says, this is what your antenna pattern looks like. And the antenna pattern tells you how well your antenna should be able to work.
And when you purchase antennas, often the manufacturer will give you a sheet of paper that shows you the pattern that it will produce.
That's right. And there's one caveat on all those papers that I want you to be aware of, and it's called this is as though the antenna is sitting there between the Earth and the Moon somewhere, even farther than that.
I
Okay.
thought you were going to write marketing.
Oh, there's
One
so,
caveat is marketing. Right?
there's so much to that. You're totally right. Yeah. But this is the pattern in free space, and that's okay because down here on Earth, it's going to be approximate anyway. So we can kind of count on that. So in free space, this is what our pattern is going to look like. Looks like a starfish. All right. Anyway, and there are some really well-known antenna patterns for ones that exist already, and you kind of say, well, my antenna is like that, so I can kind of assume that it's pretty close. So here are antenna patterns. It's the field defined by the relative strengths of signals emanating from the antenna on all directions. Well, wait a minute. What if I increase the power from Harvey right there, 5 miles away? Is my antenna pattern going to look bigger then? And the answer is no, because these are all relative. Yeah, I just drew a line out of, just because I felt like drawing a line that long. So no matter what power I put through the antenna.
Increase all those lines by 10%,
That-
it's still the same pattern.
Exactly, exactly. So yeah, all the lines will probably increase if I put more power, but it's going to be the same pattern. Thank you, Michael and Brent. Okay, so yeah, and so this pattern that you see down below is in a 3D thing. So here is Easy NEC that spit out a CSV file that's actually showing this pattern here. And I mean, that's a pretty wild looking antenna, but I mean, hey, if I can do it, they could do it, right? And this is a pattern of an actual antenna. And in fact, it looks like a Yagi antenna.
I was going to say the patterns look very different for directional antennas versus omnidirectional.
Yes. So is this, there, Michael, is this a directional or unidirectional antenna?
That one to me, given the 2D picture that I'm getting, looks to me like a multi-directional antenna.
Yeah, I would say so. It's a directional antenna too. Not very directional in one. It's got a lot of directivity in some ways, but it's kind of weird, right? So what if I did this? Yeah? Switch pins here. Here's Harvey again. Maybe a different kind. But
Harvey Jr.
Harvey Jr. There, here's my antenna pattern. Ta-da! Is that possible?
Yep.
How?
Theoretically.
In free space.
No, under ideal conditions.
If you're
Okay.
writing marketing literature.
So if I actually take one of these vertical antennas that we have on VHF radios, like the signal stick or even the Parker's J-pole, okay, and I look down on it, that's the pattern I'm going to see, just like that.
If you're looking at it from above.
See, I'm the free
See,
space.
that's the thing, it's hard to tell what
It is.
viewpoint.
And I'm not even giving and offering a reference point, so it could be anything. So yeah, and if I turned it sideways, well then it will look different, like, right? In fact, if I turned this antenna sideways, it might actually look kind of like that, huh? Which means that I've got a line going there and a line going there, like that, you see? Just like that. And this is what this antenna pattern comes from, is all these infinite number of lines coming out here to determine that pattern. Is there anything going up and down, do you think? Possibly, yeah, absolutely.
Just like the ones over there.
Yeah, I mean, on this Yagi antenna right here, I mean, it's like, number one, here's this is called the main lobe, like a lobe of your brain, right? Maybe not of my brain. My brain I wouldn't even show up on the map. But here's the main lobe. This is where this is the direction of the largest signal strength, and therefore this is the direction of the gain. When we say gain, we want to know the direction, right? The gain is in this direction, not in this direction, not in that. Okay, and then how about this lobe right here? So is there any transmission signal power going through that direction? Of course it is, okay? How about between those two? Not much. In fact, you kind of find it's kind of weird because it's like, here you got your Yagi antenna, right? And all of a sudden this guy in Oregon is like, dude, you're 20 over, you sound really good, you're booming through my speakers and everything. And then the other guy next to him is like, you know, I can't hear a thing that who is it you're talking to? Because he's in Portland, Washington, which is just a few miles away, but he's bouncing off of this signal off the ionosphere. It's like, oh my gosh. You know, so here's you know, Portland, and then, anyway, Vancouver. But I don't know. When you get...
Florida.
Yeah, when you get right between those lobes, you know, then you might get nothing at all. And people wonder, well, I thought, you know, you're talking really well to this guy over here. What's going on? Well, it could be because he's in between your lobes. Sabra.
Yes. Like, let's say you had a directional antenna and you had really good gain. And then normally the shape of the radiation pattern, I think the shape that you transmit is also normally similar to the shape that you receive. So if someone had like a vertical antenna or a horizontal antenna with like a donut pattern, couldn't it go, like the beam antenna could then go through like the blank space and then they'll miss it?
The answer is a thundering yes. So what you are mentioning is something called reciprocity. And reciprocity is a discussion that just means that the receive pattern of an antenna is identical to the transmit pattern. And there are proofs online about all that. So absolutely, and yes, Gary.
You've got a directional antenna going that way.
Yeah.
And you're trying to receive
From the rear.
from the rear. Not going to work, right?
That's right. Yeah.
Unless you
Well,
have a reflector somewhere that bounces it back to where that.
you know, I mean, if you look at this antenna right here, you can transmit in that direction and receive from that direction, right, really well. Can you receive from this direction? Maybe not quite as well, but you can, right? Because there's some lobes that are available here. What do you think, Brent?
So if you had a directional antenna like this, most of the time it would make sense to put that on some sort of motor driven or
Rotator? Yeah.
where you can position that where you want.
You know, I had a 6 meter horizontal antenna on my roof one time. I did a really funny thing. I just decided to try it out. And I had this bicycle cable going up to it, and I would crank it in order to rotate it around. And that worked really well for one winter, and it died. It got too gummed up with stuff.
If you think about it in practical terms, it's not much different than like a parabolic dish.
Absolutely.
You know, the guy on the sideline at a football game trying to hear what the quarterback says. He's holding that dish, and if he holds it just right, he can hear what's being said in the huddle.
Mm-hmm.
But if he moves that 3 inches, he can't hear anything in the huddle.
So it's kind of like my flashlight that I brought on that first day.
Yeah.
You can see it really well, but I shine it over here to Gary, and it's like, well, where'd that flashlight go, right?
Yeah.
Gary.
My understanding that the Pacas J-pole has a really good reading pattern for the 2 meters,
Yes.
that the 70 centimeter portion has an upward radiation pattern. Do you know if that's true or not? That's what I've heard.
Okay, so yes and no. So what it looks like is kind of like this. This is, let's just say that this is the 2 meter part of the Pacas J-pole. The 70 centimeter portion will look more like this.
Okay.
What does that mean?
Less gain.
Well, it's it doesn't go as far. It's not as effective as at a far distance.
At a certain direction, right? So that means right here, I've got more gain in this direction than the 2 meter. And on this one, less direction than the 2 meter.
Okay.
That make sense?
So isn't that interesting?
Yeah.
Of course, I guess we use the Pacas J-pole with 2 meters and then forget about it.
Oh, I use it for both, and I've got a lot of success. Yeah, yeah. So even the poor, gain in this direction, it might even be negative gain. Works great. I've used it so many times. I saw a hand. I'm just imagining hands.
Well, that gain refers to the sensitivity that your radio has to have to receive that signal from that given direction.
You can say that, sure.
So
Yeah.
you're going to have less sensitivity from that direction because your antenna's not amplifying that input.
That's right.
Doesn't mean it doesn't work, it just is not as strong as.
Well, and because it's on a different frequency,
Has better
you might get better reception on that frequency because it can go
and better that.
through things easier.
That's right.
Right, yeah.
It doesn't make sense to rotate.
Okay, what else have I got here? Created by addition. Oh yeah, so the reason that it works that way is because of the addition and cancellation, and I wanted to actually get it more into that. Yeah, and you just mentioned gain direction and beam width. So this antenna right here, this 2 meter, has a certain beam width, and it's very narrow. The beam width is defined by if this is 0 dB, then it's 3 dB down from that. The beam width is going to be from here to there. Whereas a 70 centimeter antenna might have a beam width that's huge. So it might have a greater beam width, which means I'm going to be able to capture a wider audience. At any rate. Let's see. Where was this leading me? Oh, right. Okay. I'm going to really quickly go back to my vertical antenna because I want to kind of cement a couple of things in your mind. And, okay, and this is a problem at my new house. It's pretty sad, but such is life, is what it is. And so at my old house, here's a picture of my old house.
I see the problem.
Yeah.
The old house isn't there anymore, by the way.
It's there in spirit. I mean, there's a field now where my house was. Anyway, so, and the differences in these two houses is the height, okay? And so what's going on is I've got a vertical antenna right here, and I've taken the same vertical antenna from my old house and put it over here. So it's the same antenna, same radio, same coax, okay? But my new house is shorter. And so it performs worse. Why? Maybe you can help me figure my problems
Part
out.
of the reflection off the ground and
Okay.
there's a lot of factors involved in that.
Yeah. Okay, so Michael mentioned one thing was, he says that there were reflections from the ground, right? Okay. That is actually one thing I wanted to mention. You had a question, Fred?
No, I was just gonna
Just
say,
stretching?
Obstruction, the lower it is, there's a lot of stuff between you and whoever's trying to hear you that might be getting in the way.
Absolutely. So obstructions, that's another really huge problem.
Fancier houses around your new house. Taller.
That's true. So here's what's going on. And I'm going to look again at the far field, not the near field. There's my antenna, darn it. And as I look at my antenna from this distance here, this is what I'm seeing. My radiation is going, let's say I'm shooting a signal out this far in this direction up in the air. Okay, should be okay. Do I have any control over that, by the way?
Yes,
Yeah.
depends on the antenna. but
So
you can-
antenna design, right?
You can change.
Are there other things maybe I can do to change my direction?
Phasing.
Takeoff angle.
Phasing is one. This is takeoff angle. How can I change the takeoff angle?
Capacitance had.
Oh, the height from relative height.
That addresses a different kind of concern. That's more feed point impedance. And that's exactly the problem I'm having. Yeah, the height above ground. So in fact, if I brought my antenna right near the ground, then suddenly my takeoff angle is going to be higher and higher and higher. In fact, this guy here, see his Yagi, what he wants is, he wants international DX, okay? And then maybe this angle is not so bad, okay? But maybe he wants a lower angle because he wants to talk to, Africa and Australia, Japan. So he needs to get that angle down some. Well, what this tells me is that this is really his pattern. That means that his antenna is too low to the ground, like mine. That's my problem right now. And so this is what's going on, is that because I'm at this angle and I'm at the ground like this, I'm hitting the ground just as much as I'm hitting the sky, aren't I? I mean, it's just a dot. So since I'm hitting the ground, I'm also bouncing off the ground, going in that same direction. But I'm going at the wrong phase. And so because they're at different phases, what happens to signals when they're at their different phase?
It reduces.
You're going to answer that, Gary?
I don't have another comment, but in a minute.
Okay. So yeah, absolutely. So what happens is these two signals will cancel each other. It's like I'm purposely making my signal weaker. That's not what I wanted, but it is what's happening because of my location. So if my antenna was higher, then my signal might look like this. So it'll still do this, okay? But in that case, the phase is going to be off a lot more, which means it'll be off 360 degrees, which means they'll actually be in phase, and they'll add, which means this will actually make my signal stronger. So that means that this will be stronger than nothing on the ground at all. And my new house is actually weaker than no ground at all. So I'm actually destroying my own signal, darn it. And people are going, no, you used to sound so good, but you sound terrible now. Okay, it's Gary.
Okay, so I got to get the wording just right, but you've got this half in-fed dipole, I don't know what you call it exactly, but you want this thing low to the ground so that you have a high takeoff, because you don't want to reach all over the place. You want to reach on the other side of the mountain. Or for example, we want to reach to Salt Lake over the ridge, right? What do they call that antenna?
NVIS.
I know it's NVIS. What does that stand for?
Near vertical incident skyway.
That's what
You're
I
going to
want
go up
to
and
say.
bounce off and come back now.
That's why we put it down really low.
Yeah, you can do
We
that.
want the high takeoff,
Mhm.
right?
Yep. In fact, you can,
Eureka, for example.
yeah, you could,
Eureka.
absolutely, yeah. In fact, some people will do that to a Yagi antenna. They'll put it, and I've done that myself, take a Yagi antenna and just shoot it straight up instead of out, okay? Well, my wife looks at my antenna like, that's not going to work. Well, all antennas work, but this one is,
You're not going to give me context.
it won't give me DX, okay? But it is intended to hit over to Eureka, and it's Eureka, by the way. So it's kind of like Manaway. Anyway, so Hurricane. And that's, if I wanted to do a close contact like that, that's what I would do. Yeah, hit it straight up in the air. Well, wait a minute. If it's straight up in the air, won't it come straight back down to me?
Well,
Yes.
we
Ish.
still have a little bit of a vertical.
And that's called what?
All I'm going to call it a
It's called beam width. Beam width. Say beam width. Beam width.
beam width.
Thank you. He's right. He's exactly. I could not said it better.
There's a little bit of that coming back down as well, right?
Well, not only that, but it goes up in that beam width, right? And it hits a dome that's flat, or is it curved? It's curved because of the Earth, right, and the ionosphere, and so it's going to come down even wider. How wide is that circle?
It depends.
It's supposed to, I remember 300 miles.
See, I like it. This guy knows 300 miles. Okay, give or take, right?
Depends on what your radiation pattern looks like.
It depends on radiation pattern and the
Atmospheric
frequency and the conditions, yeah. It depends on so many things like Michael was saying, yeah. So yeah, MVS antenna, absolutely. And I like the one that the military made. I tried that. It's like, okay, it works pretty good. And what it is simply I've got this thing, it's a fiberglass pole that's 15, let's see if I can do that right. Oh, it works. It's 15 feet high, okay, and I've got 80 meters going like this, tied to almost the ground. This is like 6 feet off the ground, 6 feet off the ground over here. And over here, I've got 40 meters that are actually perpendicular. So if you're looking on top of it, it looks like this, just like that. And the 40 meter out here, this is also 6 feet off the ground, 6 feet off the ground. And this thing works pretty good, okay, because it's low to the ground. It's actually an inverted V, not a Yagi, okay? And with that low to the ground, man, it's just shooting stuff straight up in the air. And the problem is the other person has to have an envious antenna too, but whatever. But this is one thing that's made by the military, and I never believe anything the military says, so I just had to make it and try it myself.
Put the camo netting over the top and sit underneath it, right?
You could do that, yeah. I didn't think about that. That's a great idea. Maybe that's my next POTA.
You forgot to drive your counterpoint wires on the ground.
You don't need counterpoints with this because it's dipole. But good point. There we go.
Now, would you have you calculate to make sure that you're saying that the height, there's a certain height you have to reach to bring it in phase. How do you calculate that height?
Good question. Depends on the frequency, doesn't it?
Ask him after he gets his problem solved.
No, I mean, isn't it frequency dependent, right? So that means that what you got to do then is put your antenna up there for 80 meters, just right to get it in phase. You know, do the calculation, how far off the ground. But it depends on also where you want to shoot. Are you shooting that this way or DX? If you're shooting DX, well then you got to shoot for a farther distance. And it's like, okay, that's in phase. Now it's no longer in phase. Now it's in phase again. Oh, it's no longer in phase again. It's like, oh my gosh, it's going to drive you nuts. And then all of a sudden, once you get it right, change to 40 meters. It's like, oh, I got to start all over again. So what do you do to solve that? The best you can. You know, just do the best you can.
There's no real calculation to it. It's just a try until it works.
That's right. Just do what you can until it works. There are calculations you can do, and I can show you a lot of them if you want to get into it. But it's for one condition, one angle, you know, and as soon as you change anything, it's like all bets are off.
Because if it was easy, you would have done it already.
If it was easy, it would have been called football. Okay, so yeah, absolutely. All right, all right. Why did I mention that? Oh yeah. Let's see. Takeoff angle, pattern for make or break your station. It can. I found this little blimp online, and this to me is like the ideal antenna pattern. You want an antenna pattern that looks like this for several reasons, okay? Number one, it's got huge gain, okay, in the directions you want. Number two, it's got huge beam width. See, whenever you have a huge gain, you sacrifice beam width, and so it's always a compromise. This one's got both. It's like, okay, how'd you do this antenna? I want to see this. Well,
When you want two of them, one for four of them.
no, just get a rotator. So yeah. But yeah, this is like an ideal, but it turns out to be a microwave dish. So but anyway, but it is very nice because you got huge. Okay, anyway.
But that's not too far from a panel antenna either, is it? That we use on cell towers.
Panel antennas, slot antennas can do that too. Yes, absolutely. So if my antenna, one good thing about a Yagi antenna is that it has very little gain, or like over here and so forth. You can't get much signal to be received or even transmit over there, but that means you get very little noise from there too. So all the noise you really hear is coming from that forward direction, or in some cases the backward direction. But this has really good noise rejection, is what that means. But if you get an omnidirectional antenna, well, there's very little noise rejection. You get noise equally from everywhere. So that drives you kind of crazy too. But if you can live with that, it's got advantages. Beam width is too small. There we go. Takeoff angle is too high. This is nice because, see, this takeoff angle, you don't care. It's just straight out. Why would I want a takeoff angle that's straight out rather than up in that direction towards the sky? Why would I want that down here?
Contacts are on the ground or below you.
Okay, that's one. So that's ground
or you're
wave.
targeting airplanes that are all above you.
So that's ground wave, and if I care about my local nets, that would be a good thing. But if I want something else, then what am I looking for? Okay, cricket. No worries, no worries. So
Another antenna that's equal height,
why would I want my takeoff angle down that low?
because their antenna's low.
Let me answer a different way. It's looking at the curvature. I'm using the wrong pen. I'm looking at the curvature of the Earth.
You don't go over it.
And as I'm looking at the curvature of the Earth here, then when I use my antenna, if I've got a high takeoff angle, here's my dot right there, and my high takeoff angle might look like this, then heck, I might get from Jackson, Wyoming, bounce off the ground, and I might get clear over to, Detroit, Michigan. That's great. I like it. Okay, but what if I want to get? But if I do this, I noticed also that the more hops, this is a hop that I make, the more loss in my signal. So I want to make it in one hop over to that station down there, like in this kind of thing, right? Well, look what I had to do. I had to bring my takeoff angle down lower. Well, dang, what if I wanted to hit Paris, okay? Well, that's like clear over here somewhere, right? That's like I had to go straight on the horizon almost. Look at how close to the horizon I am. Hit this thing, and it's like, all right, now I can hit Paris. Looks like an antenna tower, but it's actually Eiffel Tower. There we go. Maybe it is an antenna tower. I don't know. Anyway, so see, I can do that if my takeoff angle is really low. And the antennas that have the lowest takeoff angles are what?
Vertical.
Verticals. They are. That's why I have a vertical in my house, because I like DX. But my house is so low. So I got a lot of ground losses. But yeah, but I do make DX, well, I used to make DX contacts all the time in Europe, South America, Australia, and so forth. And you can too. So, yeah.
Build your small house on top of a high mountain.
Well, and
I should have.
We have a lovely mountain here to the east that does a good job at blocking some of that east direction.
That's true too. So,
I think maybe the heaviest ham radio guy that doesn't have a tower that I know, right?
Yes.
So the tower might help.
Tower might very well help. And I would love to if my wife would agree with it. She doesn't. So I've got to deal with what I can. Okay. And let me tell you.
That tends to be a common problem, just so you know.
Well, let me just tell you that I will be the first to say that what your wife wants comes first with me. When you guys invite me to come to your house to put up an antenna, happy to help you out. But I always want to know what your spouse thinks. Because if she hates it, I'm out of there. Okay?
You're not going to be on her naughty list.
I'm not going to have that red mark on my back. Okay?
Make sure you invite him when she's not around.
She'll let you know what
It's actually
That's
better
true.
to invite him when she is around, because
Well-
that way she feels like she knows what's going on.
Right, invited, right?
She'll allow it, and you're going to be professional. Or
Well-
professional help.
I'm just saying that, I want to be kind to your spouses and because that's important. I want to, this is a family hobby, not a one side, anyway. So I'll just make this one thing really quick and then we'll go on. Here is my earth, my dirt down here. And I'm going to say that here is my house again. I'm going to draw it on a smaller scale. There we go. It looks like a nativity scene. But here's my antenna. And it looks like right now, if I draw this, my antenna pattern for this thing might actually look something like this. Because it's an HF vertical, not a VHF. So it might look like this. So you notice that some of these lobes go downward, okay? Well, that's okay because that's some of the signal going down that's going to reflect up. Anyway, so here's I'm just making this up. I didn't measure anything for 15 hours like I said I was going to, but maybe this is what my antenna pattern looks like. But if I did what Mark suggested and I got my antenna up even higher, like up here, now my antenna pattern might look something like this. Is that better or worse?
Depends on where you want to come.
It depends on what I want to do with my signal, right? So maybe this is better because maybe I got a higher, I don't know. Maybe if I got it up here, now it might look like this. Wait a minute, I'm drawing these lobes larger now. Why am I doing that? Am I putting more power into it? Is that why? No, same radio, same power. So why am I drawing these?
Coupling with the ground, or less coupling.
I love a smart class. You guys are awesome. You know, all those things are true. Ground losses, coupling, a lot of things that I don't have down here. Suddenly I'm like in free space. Gary.
Okay, now, your old house was in Orem on the bench, and like less than a quarter mile from your house, it dropped off dramatically, and then there was a lake.
Yeah.
And then, for example, another house is like 3 miles east and near the mountains. Would that affect some of what you're describing there?
Yes.
So it could be that you're getting a different signal because you're not on that cutoff on the bench.
Like I said, I like a class who thinks.
Thank you.
Very good. What was that, Brent?
I said, and that really depends on, like we were saying, where do you want to go?
Yeah.
East or west, that's going to make a big difference.
That's right.
If you want to hit Wasatch County versus Tooele,
Then maybe I want to put an invis,
you know,
right?
yeah.
Just as an example, on our HF net, I can barely hear Noji on my end, but I can hear Carl, who's probably a couple blocks away from me, like he's screaming in my ear.
And yet,
So I'm sitting there turning my volume up and down. When Noji's talking, it's up, and when Carl's talking, it's back down.
and then we got this guy coming in from Arkansas. He comes in and says, "Dude, turn your thing down. I'm getting you 20 over." I'm going, "Yeah, but Joe can't even hear me." You know. So yeah. So yep, all the above. All right. Sir, Vern.
How much difference in takeoff angle is there between a vertical and a Yagi?
A huge difference, and it depends on frequency. It depends on height. So, but if assuming the same height and same frequency, there still will be a large difference. Okay, the vertical will almost always have a much lower takeoff angle, and than a Yagi. Yagi tends to be, you know, however, let me just say that my vertical having a really low takeoff angle for me is really nice, but you can do the same thing with your Yagi and do an even better angle because of directivity. If it was like 40 feet taller than my antenna, then it would have a very low takeoff angle and big beam width. Yagi is so much better and directivity than my antenna could ever be. So if you get high enough.
But now you've got directivity, which sometimes is a negative.
Can be. Yeah, but then you more of your signal, it gets focused in one direction like your flashlight. So it can be good too. So yes, it can be, you know, counterproductive. Yeah, if takeoff angle is too low, that can be a problem. So here's a sideways view of this. This is an azimuthal pattern, and as you can see, he's drawing it so that you have very little signal coming out this way, but over here, all your signal, and this is the point of your gain. This guy's got a takeoff angle of what? About 8%, 8 degrees, 10, 15, something like that, right? So 8-degree takeoff angle, that's really nice. Okay, and that's a Yagi too, because you can tell because there's very little signal going back behind it. Anyway, the 3 general angles of concern are the low angle for DX, middle angle for within the continent, and high angle for NVIS. So those are the main ones you want to kind of be concerned with. Hey, thanks for coming, Brent.
Yep.
I know you hate me.
Leave early.
Yeah.
It's not the discussion.
Yeah. Good. Thanks for coming, Brent. Appreciate you. Merry Christmas. All right. I just want to mention something quickly about antenna football. I hear once in a while about people who will say, you know, I'm line of sight the repeater, but yet I can hardly hear this other person I'm talking to. What's wrong? Or, you know, I'm looking down the street and I've got my radio in my handheld, my hand here, and he's looking at me, I'm looking at him. We're line of sight with each other, but we're really scratchy. What's going on? Okay? Line of sight, but no signal. What the heck is happening? And that's one of the reasons is ham radio football. So maybe I'll jump the gun on this. So here is one person. So now that Brent's gone, I can draw him this picture. Here we go. Here's his radio. There we go. He's got his handheld. Who's he talking to? Oh, he's talking to Don over there. We got 2 Dons, by the way.
You drew hair on that guy.
Okay, that's Don. Also with the radio, there we go. All right, and they're line of sight with each other. They can see each other perfectly, especially because, Brent's got glasses on here. So, but the problem is this. I'm going to now take these 2 guys, even though I've done this amazing artistry, and I'm going to put them in the far field. That means I'm going to represent them by a dot. There you go. There's Don. There's Brent. There we go. And now what we have between them is an area of transmission. Okay, and there's a field that's being generated by your radios, and it kind of looks like this. There you go. Looks like a cross between a banana and a barge. But anyway, so this area is kind of an elongated football. And this section exists because of a number of different things. One is because of multipath, reflections, things like that. And so what you find out is that anything that's conductive, like what? Water, a light pole, a truck, a water tower.
Power lines?
Yeah, a dog. Anyway, anything that's metallic or conductive that passes inside this zone will interfere with your signal, even though it's not within line of sight. I mean, line of sight's right here. Okay? But right here, let's say that a truck passes by, okay? Can that truck interfere with their signal? Yes. Absolutely. Well, why? If it's not in the line of sight thing.
Reflections, diffractions.
So what's going on is that you got, what are you going to say?
Well, I was going to say your wavelength has to cover from the top of the football to the bottom. And if something gets in the way, even though I may see just a small, my friend on the other side there, that's line of sight, but that's a small area. My wave is much bigger than that. Okay. And if a truck messes up the bottom part of my wave, it doesn't get through.
Okay. I can kind of buy that. That's not what I was thinking, but okay. That's great. So what I'm seeing is this. I've got one signal that's going directly to him right there. That's good. But I've got another signal that's doing this. And because those 2 signals are so close to each other, they're out of phase. And what do out of phase signals do? They cancel. And if they cancel, then while this truck's driving by, it's like, going by. What was that? Say it again. You're breaking up there for a second, okay? Truck. Can a flock of geese do that? Anything that can conduct electricity can do that.
That's the picket fence thing then also, isn't it?
Absolutely. Yes. Picket fencing. What are you going to say, Harold?
Is that why Simplex sometimes, so, like I live in Riverton, so I can have a guy that's, 2 miles from my house and I can hear him just fine. Another guy in South Jordan that's, half a mile away and I can never hear him. Is that what causes that problem with Simplex?
Can be. Yes, this is basically Simplex we're talking about, okay?
This is one of those points with a repeater or not.
Yeah, so here's the thing. So here I am, here's, Brent and Don talking to each other, okay? And all of a sudden they switch to a repeater frequency. And these 2 guys are 4 blocks away from each other. And they're like, man, you're so scratchy, I can hardly hear you, right? All of a sudden they go to a repeater, which is 15 miles away, and they're like, clear as a bell. Why? It's because, and here they are again, here they are. It's because now the repeater that's so many miles away up here, okay, that football is a different football all of a sudden. Okay, now that one is up in the air and there's nothing obstructing it.
You can't drive a truck through there.
It's very difficult. I've tried. So yeah.
I've got kids.
So when you got the repeater, that's why you put repeaters on mountaintops, because of this little football here. So that, okay, the one thing I did not mention, the most important obstruction of all is this. Trucks, great. Buildings, okay. But the most important thing is dirt. And what you find out is that, oh my gosh, these guys are like, how many feet off the ground is this signal? which tells me that half this signal is actually gone and eaten by the dirt. So, you know, if you eat dirt, that's payback. But still, your signal is going to get eaten by the dirt. Half of your signal is already gone just because you're standing on the ground. Well, wait a minute. Wait, I can beat this. What if I got on a
Stand on your roof.
or or ladder. Let's say if I got on a 15-foot ladder, got up there, and my friend did too. And let's say Don and Brent did that very thing, got up on ladders and talked with each other. Well, they sound better. Whereas before they sounded kind of scratchy and, you know, bad signal.
That's why we mount our antennas on the roof.
Exactly. Yes, they will generally sound better. Yeah.
Sometimes it's the radio itself.
Yeah. Well, I've rarely found that to be the case, but it is possible. So yeah, chances are your signal will sound much better, even just a few feet higher, because you got much of the dirt out of the way. Okay, so how big is this area, this volume right here we're talking about? Well, there's an equation for that, okay? So, it depends on frequency and it depends on distance. But let's just say that if you can get anything inside there that's going to obstruct, that will kill your signal. So, and this is, by the way, called the Fresnel zone. It's a French word. And the Fresnel zone will make or break your signal too. And this is all simplex we're talking about. But wait, there's more. And I'll just mention this really quickly. And that is that if you have, let's say that you have a truck that's driving by out here, that will actually enhance your signal. If you have a water tower out here, a building, flock of geese, whatever, outside that will actually help your, why?
It's a reflector difference, focusing your beam tight closer to your target.
Or what I was mentioning before was what? Why was this destroying your signal?
Because it's out of phase and out to be negative.
Because it's a phase.
The other is longer, and so it puts it back in phase.
And so actually it will constructively, what is it called?
Additive.
Yeah, it's constructive interference, right? And so because it's in phase, now it'll add to your signal. So outside of that, then it actually will help. So if you're going to drive a truck, drive it outside. Anyway, enough on that. This is, I like to call it, ham radio football, but that's what it's all about. Volume between radios, line of sight, obstructions, conductive repeaters, Fresnel zone.
This is all in 3D space too, so we're kind of looking at it from a
single
plane between 2 points.
Exactly, it is 3D space. Multipath, multipath is a very big concern for simplex, and it can be constructive outside the zone there.
So that's why the point of the mountain blocks a lot of that signal for Utah County and Salt Lake County.
Yeah, absolutely, yes. Especially, between our repeaters and West Mountain, there's a big mountain in the way, yeah. Absolutely. Let's see, I've already covered antenna height. Yeah, I like to say height is might. I always try to get it at least a half wavelength high, that's ideal. I've never been able to do that. 80 meters means how high? 40 meters. Yeah, 40 meters in the air. That's not on my property. There's ground losses, signal reflections, high as you can get it. All right, I'm going to skip this thing on trap antennas because I did a thing on it before and we can talk about it later. We talked about end-fed antennas, and I want to get to where I really wanted to end this thing with, and it's not noise.
You already talked about these things then, huh?
Yeah, pretty much.
Okay.
If you have any questions, let me know.
Thank you for letting us ask the questions when we thought of them.
So why do you want to ground your outdoor antenna? And by the way, it's law that you ground your outdoor antenna, especially if it's up in the air. Okay, the NEC demands it. If you ever find that your house burns down, and you got your antenna up there, and well, no one knows why it burned down. If the insurance company suspects that it's because of lightning and you're not properly grounded, they can actually deny your claim. So don't do that. I'll make sure your stuff is already grounded. Right, Jackson? Heck yeah. All right. So how to do it? Well, ground rod below each antenna mast. Outside your shack, install a surge protector for each coax run. We like to call it lightning arrestor. Call it what you want. Call it James if you like. But anyway, lightning arrestor with those. And a lightning arrestor doesn't not arrest lightning. It doesn't stop lightning. What it does, it helps prevent it from forming in the first place, because the lightning starts, and I've got a whole section on lightning I'm going to talk about in June, I think it is, May. Anyway, and in the club meeting. And so what it is lightning starts by ionizing the air between the cloud and the ground, or whatever it's trying to attack. And because of that ionization, you got this leader that's forming. And once this leader is complete, okay, then the static has a path to go on, because it doesn't, you have to have path, right, to go, except for an antenna. And then once it gets that path, then you got lightning and everything goes, and blinding flash and loud noise. But if you can bleed off that leader, and that's the purpose of your lightning arrestor, it'll, as soon as that leader is complete, it'll go, wait, and it bleeds that off to ground. Okay, then the lightning goes, oh, I got nowhere to go, so it goes somewhere else. It goes to Mark's home instead. Okay, that's not a perfect explanation, but you know, it's going to have to do for now. But be sure and put a lightning arrestor on all your outdoor antennas through, your coax goes through it. So there you go. You know, sometimes you just can't get it right to all the places you want. Just do your very best. Okay, this is the thing I wanted to end with, is which antenna is best for me. And I get so many questions about, well, which antenna is right for me? And the answer is, well, depends on what you need, right? Depends what you have. For HT antennas, for like VHF dual band, and always get a dual band radio or antenna. Radios, who cares? You can get, you know, anything you want. That copper cactus is a single band. I don't recommend using that for a number of reasons. One of which is it's a single band antenna. So get a dual band if at all possible, and they are very possible. For an HT, I recommend the signal stick, a Smiley. A Smiley antenna is one of these telescopic things I love because I take it to the backcountry with me when I go hiking. And when I do, like, I can reach all the repeaters out there, the snowbird and everything else, and it's so nice for a number of reasons. So the Smiley, this is a Smiley. It costs more than the radio, but it's got a flexible base. It's got a spring-loaded base here, but it's telescopic into a half-wave radiator, okay? And because it's half-wave, that's what makes it so powerful. It's so nice. But there are issues with it, like it's easy to break. I've never broken one, so people do tell me that it's easy to break. And if you get invaded by kids nearby, you can go whack, whack, you know, go away. So very nice antenna, very good performing antenna. I love this Smiley.
Is it dual band all the way extended, or do you have to shrink it to tune it for 70?
So it is dual banded all the way extended only. You have to extend it all the way. However, for 1.25, I've used it halfway extended and it works perfectly. All right. Let's see, a N9TAX, I like that. I take that on a mountain once in a while too. It's just it's made of 450 ohm ladder line. It's just a J-pole is what it is. It's very portable. Parker's J-pole, there you go. Wait a minute, Parker's J-pole for your HT? I know so many people in our valley that use the Parker's J-pole in that very configuration with their handheld. And like Ilona, W1ONA, she does that. She has a Yaesu FT60R in her room, and she connects that thing right to her Parker's J-pole, which is on the roof. That's what I do. You know? And it works. Nobody complains about her signal. She sounds wonderful. So yeah. Some people talk about Nagoya 1/4 wave whips. They work. You know, the Abri antenna. I even have one with me here. That works too. I don't recommend them just because you can do better for just the same amount of money. Here's an Abri. It's got the two, yeah, this is the short one. I got a long one at home, but I kept poking myself in the eye with it. So it's made of like a dual tape measure. But like I said, it works. It's just not my favorite. Here's one, okay, VHF again, but for your vehicle, I highly recommend the Diamond NR70H. It's a half-wave NMO antenna. Well, of course, which one do I use? Anyway, so that's the one I have on my car right now. Oh, hey, I can use this as a pointer. There you go. That's the one I use on my car. My wife actually uses this Comet SBB7 on her vehicle, and it's a wonderful. And the reason she likes it so much is because she can fold it over. Thanks for coming, Alif. And so what she does, in fact, is she keeps it folded over the entire time she's driving around. And has anybody ever complained about our signal? Nobody. Because what it does, once it folded over, it's like, okay, her radiator's gone horizontal, but suddenly it's coupling now with the body of the truck. It's like, oh my gosh, everybody can still hear her. Anyway, so great antenna for sure. A Larson 270B, also very highly recommended. Those three for your vehicle. The Tram 1180 and 1185 mag mounts are wonderful, but you know, again, not my favorites. They are doable.
And a lot of those you can also get with a UHF connector.
Yes.
Sell them in both versions depending on
Absolutely.
what thing you want to attach it to.
So what Joe was talking about is you can get a lot of these with the SO239 PL259 connector, that also called a, that's right. I like NMOs because I can pop them on and off, and they're water sealed, 2 water seals on them. Some of these other ones, if I got a base station for my vertical, like a mobile station, the Diamond 200A is a really nice antenna. I highly recommend that one. 300A is another one. I use the X510 because that's me. That's what I do. And you can hear all the way to the Idaho border, and people can hear you just really nice with that, assuming your antenna is high enough. And for VHF, my house is high enough for that, so my 510 goes really, really far. I played with GP6 and GP9s a lot in the past when I'm out with like UCARES and serving in the races and things, work really well. Also, Palker's J-Pole also has a base antenna, which my wife, in fact, uses right now. My wife insists on her own station. I remember the day she came to me, she says, honey, I'm tired of using your radio and your antenna. I'm going, oh. She's going to back out of ham radio, right? She says, I want my own unit. I went, really? Man, that afternoon, I was up on the roof and I put her whole thing in together. You can, right, exactly. Well, and then she ran the ladies net and the family history net and so forth. So she's done so much with it. But yeah, that's what she uses. Our old J-pole is almost identical J-pole to the Palker's. I think that Carl copied that, but don't tell him I said that. Anyway, great antenna for sure. The Diamond D130J, a very interesting antenna. I've installed this several times on people's houses because that's just what they wanted. It was their choice. And man, it's an amazing antenna because it does some really, so what it does is does 23 centimeters, 33 centimeters, 1.25 meters, as well as 2 meters and 70 centimeters. It's an amazing antenna. At first I was pretty incredulous and I didn't think it would work on all those bands, but I like them. So that's a great antenna. And it's only like $35, I think, but it's a disc cone, which means it's got radiator on top and it's got all these radios, like 9 of them on the bottom. Pretty nice.
How much did you say it was?
I think 35.
No, they're like 100 and something. The diamond, the diamond disc cone.
The D130?
Yeah, I just looked it up.
Oh, okay, good. So thanks, Don, for
That
the.
was pre-COVID pricing.
Okay, my memory is out of date then.
Comet makes one too, but Diamond has a better head, is rated as the better disc cone.
Okay, I've installed a couple of them. This is the one that I like a lot, just because I've played with that the most. The other ones I don't have that much experience with. So thanks for updating me on the price on that. I'm sure I just grabbed that out of thin
Yeah,
air.
it's unfortunate they had to spend that much money on it.
Yeah, but it is a great antenna. Yeah, what do you think?
Okay, the X510H.
Yes.
Possibly dumb question, but they have an X510HDN and then an X510HDM as in Mike.
Yeah, so
So one is, but
I don't know about the DM. The DN means it has an N connector on the end. Okay, the one I have is an H. I forgot which one it is, but mine has a UHF connector that Joe was talking about. So, and a lot of people like to use this EdFunk antenna, which is pretty popular because it's low cost. I'm not a huge fan of it because it works, but it's kind of fiddly. You got to play with it and get it up, and it kind of springs out of action. And,
Here's
you know.
my headphone right here.
Oh, there you go. Good.
My headphone.
Good. Good.
The purple tape modifications are...
It's my favorite color.
Perfect. All right, and then here is on HF. Now we're getting into this. So on HF, I've got verticals we're talking about. I like the Hustler 5BTV series. There's a 6BTV, the 4BTV. All of them are very nice antennas, but they require radials. The Cushcraft R9 is one that Chad uses, W7CB, and this thing is very expensive. Let me see if I get this right, Don. Okay, R9 I think is like $385. Anyway, it's expensive antenna, and it claims to be radialless, and he did not put any radials, and he's doing great.
Which one is that?
The Cushcraft R9.
$395 to keep it.
Oh, it was $10 off. All right. All right, very good. So, yeah, very nice antenna. In fact, this sounds really good on so many bands too. The Diamond BB7B is a good antenna. It's okay. It's not perfect, but it does really well. The high gain 640. I hope. See, Roy is dead, so he can't argue with me. But he has the 640, and it doesn't work that great to me. And what's the other guy's name? Sean. He has a 680, and it's like, it works okay. Okay, but he mixed it up by an amplifier. So anyway, so it's again not my favorite antenna, but it does work. The 680, the problem with it is it requires a lot of height. And so when he raised that thing up like 40 feet in the air, that's pretty far up. And then it started working a lot better. So it requires a lot of height. Here's some more. So multi-band types for HF. Wire antennas. The Buckmaster DX-OCF, that's a very nice. If you want to do a wire type of antenna, that is probably the best wire antenna I've seen in a long time. The Palomar OCF 4010 is another very, very good wire antenna. And again, OCFD, off-center fed dipole. The Alpha Delta DXEE, the DXCC, the DXDD, those are all wire antennas. The EE and the CC are parallels. The DD is trap. Thanks. It's a trap dipole. So if you want to get a trap, that's available. You can actually buy it. But at any rate, Alpha Delta makes all kinds of great antennas. Most of them seem to work really, really well. But really, if you're going to make a wire antenna, I recommend you actually do it yourself. Just make one.
It's not hard.
It's easy, it's cheaper, and it's a great experience. Vern?
Is the off-center the same as the Wyndham?
So a Wyndham antenna is interesting because it also, kind of like a G5RV, it's a cross between that. So what you've got, a Wyndham antenna is an off-center fed dipole, but it's got a ladder section too that matches. And so that ladder section is for matching. And so at the end of that, then you can, however, there are Wyndhams that you actually use coax for matching too. So they have that available. So almost. So it is an off-center fed, yes. My antennas also make one. I have one of those. I have my antennas end-fed half-wave 8010. It's not my favorite. It performs okay. You know, it's not bad. I do like the Buckmaster better. End-feds in general I have a kind of a problem with because you really got to play with those things and get them right. I used the 1982 MFJ from during like our 76ers picnic when we did that at Highland Glen Park, and that's the one that Karen she was so excited she got onto the USS Iowa with that antenna. She's like, oh I want to get onto this, you know, and do HF, and that's when she got her general license, and she was so excited. Anyway, so. And here, let's see, more multi-bands. But this is for like a vehicle. If you're going to put a HF antenna on your vehicle, I recommend that if you have a Yaesu radio that you use an ATAS 120A, it's made for a Yaesu radio, and that's because it sends signals through the ground and other things like that to the antenna, and it just goes. So it's kind of a screwdriver type of antenna that raises and lowers by a little motor in there, and it works really nicely. It is a bit expensive. A Tar Heel is even more expensive. I've never used one of those, but I hear that it works really well.
I've got one in my car in the parking lot.
Does it work?
Works great.
Great, there you go.
In fact, I used to have the Tar Heel too.
Okay.
And I got a smaller car now, so I've got the smaller version.
So what radio?
I have the Yaesu 891.
891, great.
I like the Tar Heel because I think it's more expensive. I think it's built more robust. I also manually tuned it.
Okay.
So
great.
About compatibility because I just do it myself.
Good, no, I like it. And a lot of people like to do the Chameleon MPass too. It's a very favorite of many people. Mike?
So that first one, the Yaesu
ATAS.
ATAS one. I thought I had read somewhere people are using those like on their houses, that they're not necessarily a car one.
Okay, so those of you who knew Roy, okay, put an ATAS on his house too, and it never worked for him. And when I went up to take a look, it's because he didn't have a ground plane. And that thing needs a serious ground plane. So when we moved that thing over to his aluminum awning, then it's like the whole world was at his fingertips. It works really nice. Then he died.
Great as long as you ground them correctly is what you're saying.
Yeah, the ground plane is there. But then he died, so it doesn't work anymore. But yeah.
I've got a Tar Heel high power.
Okay.
Mounted on the ground behind a tree.
On the ground?
HOA.
Wow.
So I've got like next to my gutter, behind a shrub. And it, it works really, but it works. But
good.
I mean, if it was on top of my roof, it would work great. I got counterpoise out on it. I can manually tune it from 10 meters to 80 meters.
Cool. I like it. Okay, we're just about out of time. And so, which antenna is best? Well, how about a beam antenna? If you're into one of those, I recommend these three manufacturers. Mosley, which is to me number one. The angels speak whenever you say these words, like Mosley. Okay, anyway, that's what some of the best antennas. This picture, those of the Cushcraft A3S, probably one of the most popular antennas in the whole world for Yagis. It's very nice, and you can see right there they have these little thingies on them. Those are traps, and those traps make it so that there's multi-band. Anyway, SP7GXP, another one, good manufacturer. Not my favorite, magnetic loops, G5RVs, ham sticks, Wolf River coil, super antenna. I had a super antenna for a long time, and it finally shattered on me, but I made a few contacts. I highly recommend against doing the isotrons or Moxons. They're just a pain in the neck. To all of you who have Challengers, the gap antennas, all due respect, but I don't recommend. They are very difficult to work with, especially because they're made of 10,000 parts and it spends a year to put them together. When you finally do, you got to retune them by taking them apart and putting them back together again. Okay, others, there are slot antennas, head antenna, horizontal loops, rhombic antennas, and so forth. And that's it, the end. Good luck to everybody. There is a quiz at the end. Well, maybe not in here, but at any rate, I wish you luck on all your antenna things in the future.